So, have you ever really stopped to think about it? What actually makes a solid a solid, or a liquid a liquid? I mean, we get that gases are just particles zipping all over the place, but what's stopping the molecules in your water bottle from just flying away? What's the invisible glue that holds our entire physical world together? Okay, let's dive in and figure this out. Here's the game plan for this explainer. We're going to start by uncovering that molecular glue, the forces between molecules. Then we'll actually rank them by strength. Think of it as a stickiness scale. After that, we'll see how that stickiness plays out in the real world. And finally, we'll pull it all together onto a map that shows how matter behaves under pretty much any condition. All right, first up, let's get right to the heart of it. What really is the difference between these states of matter? Well, it all comes down to this constant battle between energy, which is always trying to push particles apart, and attraction, which is trying to pull them together. Okay, so check this out. It's such a perfect contrast. On the left, you've got a gas. The particles have so much kinetic energy that they've totally won the battle against attraction. They're just flying around doing their own thing. But on the right, in a solid, attraction is the clear winner. Those particles are locked into this rigid, ordered structure, pretty much just vibrating in place. And liquids? Well, they're that beautiful, chaotic middle ground where particles are still held close, but they can slide past one another. Which brings us right back to our central mystery. What is this invisible glue? What are these forces of attraction that create liquids and solids? What chemists call the condensed phases of matter. And here it is. The answer is intermolecular forces, or as you'll often hear, IMFs. Now, it's super important to get this straight. These are not the super strong covalent bonds holding atoms together inside a single molecule. Nope. These are the weaker but incredibly important forces of attraction between different molecules. They are the glue. Okay, so let's keep building on this. It turns out that not all this molecular glue is created equal. There's a definite hierarchy, a ranking of stickiness that explains so much about why different substances behave the way they do. Now we're going to focus on the big three. At the very bottom of the ladder, you've got London dispersion forces. These exist between all molecules, and it's all because electrons are constantly sloshing around, creating these tiny, temporary magnets. A step up from that, you have dipole-dipole forces, which you find in polar molecules that have permanent positive and negative ends. And then at the top of the heap, we've got a special, souped-up version of that called hydrogen bonding. This is the big one, and it happens when hydrogen is bonded to a really electronegative atom like oxygen, nitrogen, or fluorine. So here's the bottom line, the thing you gotta remember. London dispersion is the weakest, dipole-dipole is in the middle, and hydrogen bonding is by far the strongest of these three. You can think of it like tape. Dispersion forces are kind of like a sticky note. They're there, but they're weak. Hydrogen bonds, that's like duct tape. And wow, this chart just lays it all out perfectly. You can see the real-world effect right here. I mean, look at fluorine. It's only held together by those weak dispersion forces, and it melts at a crazy cold -220 degrees Celsius. Now, compare that to water, with its powerful hydrogen bonds melting at a familiar 0 degrees. The stronger the force between the molecules, the more energy it takes to pull them apart, and that means higher melting and boiling points. It's a direct link. Okay, so we've got this hierarchy of stickiness down. Now for the fun part. Let's see how it explains all these properties of liquids that we can actually see and interact with every single day. We've all seen this, right? You try to pour honey or motor oil and it just moves so slowly, way slower than water. Well, that property, that resistance to flow, has a name. It's called viscosity. To put it simply, viscosity is just a liquid's internal friction. It's all about how easily the molecules can slide past one another. And the connection here is totally direct. The stickier the molecules are to each other, meaning the stronger their IMFs, the harder it is for them to move around. And that means a higher viscosity. It just makes sense. Here's another one you've absolutely seen. That amazing beating of water on a freshly waxed car, or how some insects can literally walk on a pond. That's not magic. That's the power of surface tension. So what's happening here is that the molecules on the surface are getting pulled inwards by all their neighbors below and to the sides. See, a molecule in the middle of the liquid gets pulled equally in all directions, so it's balanced. But one at the surface gets a strong net inward pull, creating this kind of tight, elastic skin on the liquid. And yep, you guessed it, The rule is simple. The stronger those intermolecular forces, the stronger that inward pull is, and the higher the surface tension. It's all connected. The very same invisible force making oil viscous is what lets water form those tight little beads. Okay, let's tackle one more property. You know how if you spill a little rubbing alcohol, it seems to vanish in seconds? But a puddle of water can stick around all day. That huge difference comes down to something called vapor pressure. So, imagine you've got a closed container with some liquid in it. Some of those liquid molecules are always going to have enough energy to escape and become a gas. That's evaporation. But as the gas molecules build up, some of them are going to get recaptured by the liquid. That's condensation. When those two rates become equal, you hit equilibrium. And the pressure from that gas at equilibrium, that's the vapor pressure. Now, here's the twist. With this property, the relationship is actually the opposite. Think about it. If the molecules are really sticky and held together by strong IMFs, it's way harder for them to escape into the gas phase, right? So you end up with fewer gas molecules, which means a lower vapor pressure. It's the same hydrogen bonds that give water its high boiling point that also give it its low vapor pressure. All right, we've seen how this stickiness affects all these different properties one by one. But what if we could put all this information, solid, liquid, gas, and all the transitions, onto a single map? Well, we can. This right here is a phase diagram, and it's one of the most powerful tools in all of chemistry. All you do is pick a temperature on the bottom axis and a pressure on the side axis, and this map tells you instantly what state your substance will be in, solid, liquid, or gas. The lines between the regions show you exactly where phase changes, like melting or boiling, happen. And of course, every map needs its key landmarks. The triple point is this one-of-a-kind specific temperature and pressure where all three phases can exist at the exact same time in perfect equilibrium. It's wild. And then there's the critical point. If you go beyond that temperature and pressure, the distinction between liquid and gas just disappears into this weird state called a supercritical fluid. So let's just bring it all home. The strength of the intermolecular forces, that molecular glue, is the master key. As you make that glue stickier, as you increase the strength of the IMFs, you get higher boiling points, higher melting points, higher viscosity, and higher surface tension. The only one that goes down is the vapor pressure. If you can grasp that one core concept, you can unlock the behavior of almost all liquids and solids. And this all leads to a really mind-blowing thought. All of these huge, macroscopic properties we see, from the way oil flows to the temperature water boils, are all controlled by these tiny, invisible forces between molecules. So if we can truly understand and master these forces, does that mean we can start to design and build brand new materials with any set of properties we can possibly imagine? The possibilities there are just amazing to think about.